So we will talk about time and clocks in distributed systems. And specifically today, we will talk about why you would need, in certain cases, a better leader election algorithm than what could be provided in a partially synchronous system. So let us talk. So there are two algorithms that we are going to first motivate the use of physical clocks. You know that every processor has its own physical clock. And we do not assume any kind of synchronization between clocks because it is impossible to get an exact synchronization of clocks. So that is, but we'll start by thinking about why, if we have these physical clocks, could we do something better than we did before? For example, in the asynchronous systems or the partially synchronous system. And that is what we are going to discuss today. And for this, we are going to look for two algorithms, one in this lecture and the next in the next lecture. So this lecture will be about time-based leases, or leader election, actually, in a sense. Okay. So we'll extend a little bit the model that we have. So as you can see, our model, so we assume that we had asynchronous model. In this asynchronous model, we have computations. There is no bound on the time to take a computation step. And we also assume there is no bound on latency in the network. And that was the asynchronous system model. But now we are going to also introduce clocks in our system. So clocks. And by assuming that processors have clocks, can we exploit these clocks in a better way? So that is what we are going to do now. So by having clock, we are getting a model which is a little bit having more properties than the asynchronous model, but it's actually very, very weak model. But it will lead to that we can do some of the algorithms that we do in distributed systems in a little bit more efficient way. And that's what you're going to see now. Now, I'll just put this quote from Google, which says, if we can exploit clocks in a distributed system, why shouldn't we do it? In fact, he says the following is that our machine statistics show that bad CPUs are 6 times more likely than bad clocks. That is, clock issues are extremely infrequent relative to much more serious hardware problems. Okay, so let us exploit the clocks that the processors have. So the question is, why do we consider algorithm that uses clocks? Okay, this is the point. So maybe, and that's what we're going to show, by making strong assumption about the system, we can get better efficiency or performance. It means basically, we might, in certain cases, get a better or more efficient algorithm if we can use clocks. But this model is fairly weak in the sense that we still cannot solve problems that are not solvable in the asynchronous system. For example, the impossibility of consensus still holds, and it needs this partial synchrony or eventual synchrony to be solved. So we still cannot solve this, but we can have certain abstractions or certain services with some better properties. And that's what I'm going to show. Okay. So here comes one of the algorithms. If we look to leader election in general, if you remember even the ballot leader election or the eventually, what's called eventually perfect leader election, or so these algorithms actually does not, it has a following property, that you might have two leaders overlapping at the same time. In some period of time, they can overlap. But when the system eventually becomes synchronous or stabilizes, there is only one leader. Now we would like, actually, we could implement another algorithm which give a little bit stronger leader election properties if we have clocks. And this algorithm is what we're going to discuss now. What is the properties is basically, we would like that whenever a process is elected as a leader, it is guaranteed that there are no other processes now that consider themselves as a leader. And also, not only the processes that consider themselves as a leader, but also the followers of these processes. So the followers follow always one leader at a time. And this we can achieve if we have clocks. And that is what we are going to show in this lecture. So, but let us see the problem now first. So there is an opportunity for optimization. If we can use clock, we are going to show an algorithm for that and see an argument why this is maintained. That will be really basically the whole lecture. But let us see what we have achieved until now. So assume we have a key value store implemented by a replicated state machine. Okay, and you know, a replicated state machine is implemented by a sequence consensus algorithm like sequence packages that we described, or by raft. Okay, and you could take you could use it to implement a key value store by basically partitioning or sharding the key value store and having a packages group for each shard. Okay, as long as you just do operation on a single key at a time. Okay, so let us do that. And so we have this key value store. It is implemented by a replicated state machine. And let us assume it supports only the following commands. You can do a read with a key. It's like a get from a key, or write on a key. It's like a put or something. Sometimes it's called put. Or you can do more complex operation. And here is which is compare and swap operation. So let us see what is just to remind you what is a compare and swap operation. It's an atomic operation that requires both read and write atomically. Okay, so what is a compare and swap? So we can see it here. So compare and swap will take a key, will take an expected value and a new value. And a compare and swap will write the new value if the old value is the expected value, only if the old value is the expected value, and it will return the old value. And why do we need compare and swap? Because with compare and swap, you can in software implement locks. You can lock certain items, you see. So that is why we need that. So we need here, this is just want to emphasize, we need a replicated state machine. Because if you remember the lectures on shared memory, the shared memory can only implement strong consistency like linearizability only with read and write operation. It cannot implement compare and swap. This is an operation that cannot be implemented by the shared memory model in the asynchronous system. And that's why we need consensus, and that's why we need a replicated state machine, and so on. So let us assume just the service that we have now is based on sequence paxos or in graph, doesn't really matter. And let us see how things work. Okay, so we assume we have a paxos replication group of 3 processes, P1, 2, P3. And any one of these can act as a leader, and then it will also acceptors and learner. That's not the normal case in a replicated state machine. Okay. All right. So the key value store is implemented by this paxos group, P1 to P3, and then we have a number of clients. We call it pi sub c here. And we assume the network is stable, and P1 is the leader. Okay, so he's the leader. So now clients can talk to the leader to perform read, write operation and compare and swap and so on. Let's assume that. Okay, so so let us look here what happens normally. So for example, we have a client, we call it P4. It wants to execute a command, so it will send a request to P1. P1 is the leader. So what P1 is going to do is trying to decide this command, okay? It's trying to decide this command eventually. And once it decides the command, it will inform the client that the command is now performed. It does it by trying to send and accept messages. This is in general case, or pipeline accept messages, and it's going to get replies, which I will call it message number 3. And then after that, it will now this command is chosen and it's decided, so it can answer the client that it is done. Okay, that's what's called P4. So what do we have here? We have the following situation. We have P1. Oh no, we start with P4 instead. It sends a first message to P1, which is the leader. P1 consults a majority, which could be P1 and in this case P2. And once it gets this second message, this third message, P1 gets this majority. It knows that now this command is decided or committed in the other, if we use draft terminology. Now it can send a result to P4. So even if these Paxos group pipelines messages, but the latency for the client, which is P4, is actually 4 message steps, as you can see here. But the Paxos group itself, or the replicated state machine pipeline, all of these things, but we have a latency of 4. So I hope that you understand this, okay? So let's continue. So now we have, what happens, so observe this was a very interesting thing here. So this is about, in general, any command. So the question comes in, what happens if the client, his command is a stateless command? What I mean by a stateless command, it is a command that does not change the state of the system. Like, for example, P4 want to read a variable X or a key X. And of course, the leader, he has it, P1 has it, has the right value. Why he has to go through all these 4 steps just to give back to the client, here's the value. So that is what we have. So assume that we have a situation where we want to do a read. Wouldn't be better, in a sense, that just P1 directly responds with the value of the variable X immediately, or the key X immediately? So like this, okay? So P1 store the entire state, as it's written here. So P1 can basically read the state variable X and respond immediately. So here's a question I'm asking you now. Now you can you can unmute and answer. If this is possible to do or not, assuming that we want to guarantee the strongest consistency model, which is linearizability. Any answers? Anybody wants to answer? Harold? No, he's not here. I said. So I don't hear you guys. So are you with me, or let me just stop the sharing now for a second. Hello?
Hi, I have an idea, but I'm not sure whether I'm wrong, whether I'm right or wrong. I'm thinking about this, like the system, like the real network, in the real world, and like P4 seems like to be a client, and P1 seems like to be a CDN in the real network. So in this kind of thinking, I think P4 can read the message from P1 directly.
Very, very good for your answer, and I will now go back and put the screen share again, and we will.
But I'm just thinking from the aspect of the internet working, but I'm not sure whether it works in the same way in a distributed system.
Yeah, so I will actually answer this. It will work for certain. So the answer shortly, it will work for certain consistency models, but not for the strongest consistency model, and I will show you. Okay. So it will. You studied. You remember you studied the consistency conditions called sequential consistency. For that it will work, but for linearizable consistency it will not work. And I just want to show you that. So okay. So that's where we are. Good. So I mean, you would like to have that, don't you? You don't want to have 4 communication steps just to read a value. That is, you would like to have that. So let me show you now what can go wrong, and you will see it here. So assume that we have a network partition, which is in this network partition, P1 with 2 clients are in a group, and but P2 and P3 with other clients are in another group. So this is split, and this is a network partition. Always, I can call it. It follows the asynchronous model in the sense that this will happen temporarily. It will disappear, but the network partition happened now. So in this case, if you think of P1 thinks he's a leader, okay? But now P2 and P3 discover, if you even have a ballot leader election algorithm, discover that P1 is not a leader, and they will elect a leader, and that assume the leader will be P2. Okay, so P1 thinks he's a leader, but now we have 2 processes think they are leader, P1 and P2. And normally, nothing will go wrong if you do these 4 steps of communication, because if P4 requests a read, and so P1 tries to get the read decided, it will not get decided, because he does not have a majority of other replicated state machines to do that. But what we have now is the following situation. So P2 is elected, P1 never hears about it. So now this sequence of operation happened. P9, which is this process, wants to do a write, okay? So it will request a write from P2. P2 will communicate with P3 and execute the write because he has a majority. So now at this stage, we have modified the value of X, okay? So in this sequence of execution. After that, P1, who's unaware of the split, of course, got a request from P4. And then if we do as we said, he thinks he's a leader, so he thinks his value is up to date, but his value is not up to date. But he will send this value to P4, basically. So now we have a situation with the value of X sequential. I mean, if you think in a linearizable order, the value of X has changed, but P4 is reading an old value. Does everybody follow this? Can you maybe say yes or something? Just put on the microphone.
Yes, it's clear.
It's clear. So why? Because if you remember, the operation that is done by P4, which is trying to request a read, which is a request, and he gets a response. All of this happens after there is the operation, the write operation has ended. So it's really coming after. So this is actually violates linearizability, as you see here. So so somebody will say, so who cares? It's still, actually, it does not violate sequential consistency, because sequential consistency say I can find a sequential order of all these operations, but this sequential order has to respect each process, its process own process order or sequential, the order of operation on each process. It does not have to have a global, a unique global sequence of operations. So that is what is sequential consistency is. So the question is, okay, that's fine. You can do it well like this, as long as you say your system will support sequential consistency, but not linearizability. So now I want to ask you a question, which is might be interesting. This is a question now for discussion. So why we would need sometimes linearizability in a database or a key value store and not sequential consistency? I will open it for you. Can you put your unmute and tell me if you have anybody? You can say either I don't know, or you can say, I know, I have an idea why sometimes we need linearizability and not sequential consistency.
We might have,
yes?
we might have really important data we need to distribute that cannot be.
I can help you a little bit with this. The following, I will add some information. Quite often when you do an operation on a database or a key value store, it will trigger other operation as a side effect of it, not on the database or the key value store, but in the system. So this is just give you some example. Now you can answer, but I can tell you why. This is sometimes called external serializability in database community. And the reason is actually the following, is that if the order operation is important, if you, for example, you trigger operation that creates side effects, and again, we'll give you some example for this, okay? The following example could make sense, okay? That you don't want to read an old value. Assume the so-called write operation that we did with process P9 was actually an operation. Its side effect, the triggering of it, is to delete one of your friends from your friendship list, okay? And assume that after that you wrote something about that friend, which is not nice. Okay? So it might be very well that P4 will still think he has all the information in the system. So all the information, he might be in the same friendship list. So he might be able to read this subsequent information. So what I want to say that sometimes linearizability has more important if it can trigger external action. And this external action, you would like to have them happening in a strict order, specific strict order. Do you follow my example? Can you say yes or no?
Yes, so when we have dependencies between values and updates, then we might need to ensure the same order between those operations.
Yeah, because it does change, it has some effect on the external world. If your system is made such that it will trigger operation on the external world, then you will need this linearizability consistency and not only just sequential consistency. You see? So it depends on the context where you are using a key value store in this case, or a database. You see? All right. Shall we continue? Okay. So
yes.
Yep. All right. So now, here is a problem again. The reason P1 cannot respond to its current state because some other replica may have assumed leadership and modified it without P1. We have did that. Is there a way to avoid this? Of course, the first way is to try to say, when P2 wants to become a leader, he has to communicate with P1, but P1 is partition, so this does not work. So, but we can solve this problem. This is a very interesting thing. So it cannot be solved So here's a very interesting just result here. This problem cannot be solved in the asynchronous model or the partial asynchronous model without having some form of a notion of clock and time. So you need this extra little bit extra properties. So we'll do something called time leases instead. And let me show you a little bit. Solution is time-based leader election, basically. So what is that we would like to have? We would like to have the leaders to be disjoint in time. Now we're just talking about time as an abstract concept, physical concept, not about clocks. We're going to talk about clocks a little bit later. That is one thing. So here is what we want to have, actually. In a Paxos group, which is a replication group, talking about physical time, we would like to have only one leader at any given time. Not only that, we would like also to have the following situation. We have leaders and followers. So we have also talked about the followers. We would like that the situation where if a process, this process called Q, is a follower for that leader P at time T, then there is no other process that can be leader at time T. So it's not only that the leaders are disjoint, but also followers are disjoint in a sense. So you can be here, as you can see from this example. So this is in the first period here, P1 is a leader. So this is a time axis, this is time. So Q is a follower of P1, only in this period. Q and other processes too. And now, in this period, P2 is a leader. It's disjoint in time disjoint from P1 in time. And any followers will be at this period only followers for P2. Okay, so this is the property that we want. This property cannot be achieved if you have partially synchronous systems when you have leaders and have eventual leader election, whatever it's called. Okay, you cannot. All right, we continue. Okay, so here is at a very high level. Now we're just talking about time, but then we're going to talk about clocks a little bit later. So the idea is as follows, okay? And when P becomes a leader or wants to become a leader, for example, you use a ballot leader election, becomes a leader, then he will send a request, prepare request. But this is very interesting because now he will not be only requesting, of course, that is a leader that if you look to the general Paxos algorithm, the leader comes with a number, and that will be, and then the other processes, I will just use the word followers here, will follow the leader by promising not to accept anything with a lower than this number from anybody, but that's not enough. So in fact, the followers, which are in this case acceptor, in fact, will grant the leader and say, okay, so the leader will not only send, I want to become a leader, here is my ballot number or something. He will say, I want to become a leader for 10 seconds. And this is my ballot number. The other processes will say, okay, we will say, okay, you are the highest proposal that we have seen right now. We will give you this promise not to accept any other process with a lower ballot number, but also only for the next 10 seconds, okay? Or even, I said it wrongly actually. We will not accept anybody else as long as you have the higher ballot number now in the next 10 seconds. Even if those other guys come with a higher ballot number, okay? So we have two conditions now to accept a leader. One is it is a higher ballot number right now, and I am not accepting from other leaders before that. And now I will give you a grant for 10 seconds, and I will not accept any other request to become a leader during these 10 seconds. That is what. So here, if a proposer gets leases, that's what I'm just saying here, from a majority of acceptors, then the proposer will hold a lease and become the real leader. Okay. In this time, the first acceptor until the first acceptor lease expires, the leader or the current proposer knows that there are no other proposers that can hold the lease on this group. So let me show it in this picture. So you can see here, P wants to become a leader. He says, okay, he will send to the followers now, I am the leader. Oops, just a second. This is all right here. A follower at time 2, in general, will get the request from the leader. So he will grant, so Q will grant P, the leader, a lease from his time that he got this message, which is T2, until what? Until T4, which is T2 plus 10 seconds. While the leader himself will start counting on the time from T1 until this point, which is T3, which is T1 plus T3. Okay. So let us do it again and say it more exact in the Paxos terminology. So time-based leader can be integrated in the Paxos messages. So as before, acceptors join round N by sending a promise in response to the prepare. And the promise was before not to accept proposer in lower rounds. But now, what we have in addition, we require that if Q joins round N at time T, then Q promises also not to join a higher round until 10 seconds has passed, 10 T plus 10, okay? So now we have two conditions to accept a leader. And now, if the proposer or the whatever he's trying to become a leader here gets promises from a majority, then P knows that no other proposer can get a majority of promise during these next 10 seconds. So he is guaranteed during the next 10 seconds to be alone as a leader if he gets promises from majority or responses from majority in general. Okay. So this is the general idea. The general idea says, okay, now I can become a leader if a majority accepts me, and the majority can accept me because I have a higher ballot number or something like that, but also they accept me for 10 seconds. And they promise me not to go and become a follower of any other leader during these 10 seconds. Okay, that's what happened. But notice now, we are actually talking about physical time interval, and not about clock values. Clocks is a device in each process. This device, basically, you can think of it as a function which maps physical time to clock time. Okay, so that is, and it's monotonically increasing, I would say. But now we'll have two problems. First of all, and we'll see if we are solving these two problems correctly. One is that we have two issues into account, which is we want to use clocks, not physical time. So because we don't have physical time, we have only clocks. First of all, we know that our network is asynchronous. And we know something which we will go into detail later after the break, which is something called physical clocks do not really exactly mimic real time. But and different clocks can drift away from each other by the number of ticks they can do by, say, absolute 1 second. One clock maybe it should do 1,000 ticks, but another clock can do 1,010 ticks in 1 second. So they are not really, so the clocks can drift away from each other, the values of the clocks. Okay, so we'll address these two problems. The asynchronous network problem is easy, as you will see now. So P, in this case, wants to be a leader, and Q should be a follower. P sends a prepare message, okay, or a request to become a leader, and he was expecting now a majority. The message arrived at Q at time T1. And he now, at this point, he has a majority of promises or majority of acknowledges, depending on the algorithm. So at this point, he knows that he can start to become a leader. Before that, he doesn't know. He has to accept the majority. Okay. This time we call it T2. Now, from the perspective of a follower, he doesn't know how long time the message came from, I'll put it this way. From perspective of let us put it this way. What do we have here, which is guaranteed? We have that T0 is less or equal T1, T1 is less or equal than T2. Okay, that is, I guess, is understood. From Q's point of view, this is Q, he doesn't know when P1 send a message. He doesn't even, it could be extremely good network that the message has arrived somewhere here, or it just has arrived here. So he doesn't know. So the only thing he can assume, it is from this time, he will add 10 seconds until this time and say, okay, during this time, I am granting you P to be the leader. Q, on the other hand, he cannot know when this response has arrived to him. He can just, the network could be extremely fast. It could arrive here, here, or somewhere. He doesn't know. So from P's point of view, he can only have a lease in this period. I mean, from T0 to T3, which is T0 plus 10 seconds. Okay. Now you can see the effective period where P is a leader is this period only. This period. No, this period only, sorry. Yeah, this period, exactly. This is where things can happen. Okay. If the network is very bad, the period I just mentioned could become smaller. If the network is very good, this period will be near the 10 seconds. Okay. So for example, if you have milli or microseconds message traversal, then it will be nearly the same time. Okay. So here's what is what is written in this slide. Yeah.
You said that P could be the leader from T1 till T3 effectively.
Yes.
But at the point T1, P doesn't know that it is a leader.
T1,
so
no.
I would say
no.
P
T1
can be the leader only from T2 till T3.
Okay. No. P does not know he's a leader at T1 because he doesn't know T1. T1 is a time at the follower Q. He only gets the message.
Exactly.
Mm. So you are completely right. I'm sorry. The effective period is this one. Yeah, you're right. The effective period is this one, right? That's what you are saying.
Yeah, correctly.
Yeah, of course. Because I mean, he will not become a leader really until he gets a majority anyway. You see. So he will not be performing any operations until he gets a majority, and the majority start from T2 to T3. You are right. No, it's correct. I just said something wrong. Okay. Do you agree on that? Do you agree on that?
Yeah.
Okay.
It's fine.
Yeah, great. Very good. So in any case, so P1 has to be conservative. So he assumes, as you said, and assume T1 is equal to T0. So anyway, he starts his clock here, T1. But he will not, this is a wasteful period. From T1 to T2, from T0 to T2 is a period where he really cannot use his leadership to do anything, I mean, productive in a sense. Okay. Okay, so now we, but okay, so that is, sorry, that was how that is how we handled the asynchronous issue of the network. The next issue is actually clock drift. And I'd rather take a break now and we talk about clock drift from 2 o'clock. Does that make sense? If everybody agrees on that, we start again at 2 o'clock?
Yes.
Because then we can cover this topic completely. And even maybe we'll end anyway about a quarter an hour before. All right, so let's meet at 2 o'clock then. Okay.
Sorry, Professor. I'm afraid you mute yourself.
Yeah, now I'm. Is it okay now? Yeah. Do you hear me now?
Yes,
yes, much better.
Good. So okay, so sorry, I just muted myself while we were in the break. Okay, so any questions before we continue on the time lease, the thing that we discussed in the first part? Because we have time, so if you want to discuss, we can do that. Any questions? Anybody has questions? No or yes?
Professor?
Yeah, before we continue on the time lease.
Yes, I do have a question, but it's not about the first part of today's course. It's actually a proposal for the final project report. I mean, can we have a voluntary discuss session after the final project report, so maybe we can compare and discuss about our implementations of the final project?
I see. Can you send this information to Harold, because he is really the course assistant, huh? He can actually add some session on that, huh? And just put it in the discussion, or because it will be Paris and Harold will take care of that, huh? Is that okay for you? I don't know if Harold is still here. So no, he was doing something else, so I don't think he's in this session. Can you propose this again? Can you propose this?
Yes, sure, I will.
Yeah, exactly. And propose it just after this lecture immediately. Yeah? And specifically because the projects are, I think, is it only Harold now that he's taking care of all the projects, or not? Or is it Paris, or is it somebody else? I'm asking. Can anybody answer?
Max is taking care of the Compix project.
Max is taking care. Okay, I see. So maybe the question should be directed both to Harold and Max. Exactly. Oh, very good. Okay. All right. Shall we continue? Okay. So we'll discuss the other issue that we didn't discuss. First was the asynchronous network, and we knew that if the network is asynchronous, depending on how fast messages propagate in the system, the period of the lease will be a little bit less at the leader, a little bit bigger or longer at the followers. Huh? You have seen this in the slide before. Okay, so let us go now to clock drift, which is the other problem. Now we talk about clocks. For the first time, we are talking about clocks here. Okay, let's see. So here's the issue. To understand the issue of clock drift, we have first to describe clocks and time more formally. Otherwise, we will be talking about things that we don't really understand. So what is formally a clock? And that is the point. So a clock at a certain process, say process PI, is a monotonically increasing function from real time to some value, some real value. Okay, so for example, that is the only thing. It is you can think of it as a function that always monotonically increases, and it should reflect. So it should reflect the real time, and if the clock is more accurate, when a clock ticks 1 second, assume just it takes actually milliseconds or microseconds, but if it takes 1 second, it should more or less reflect the time, real time has passed 1 second, okay? At least in a frame of reference where everything is stationary. We don't need to go to relativity theory, okay? That's fine, okay, good. So what we have now is at each process will have a clock. So process PI will have a clock called CI. And this function, CI, it's a function. It takes time and produces the clock time. So it's a function from real time to clock time. And the function, what is real time first? So real time itself, what is it? So real time is actually defined by some time standard. Okay. And this time standard is called coordinated universal time. Now, how real time in physics are defined is by finding a stable reoccurring phenomena, and this phenomena can then be used to measure time. Okay. And what this coordinated universal time does, it's defined as follows. So we define what is a real-time second is. And it tells you that the real-time second is the duration of a very large number of periods, and a period, think of it as a sine wave, like this, and a period is from this point to this point in a sine wave, for example. For example, just think of it this way. A large number of periods of radiation corresponding to a transition between something called hyperfine levels of a ground state of certain atom, which is the cesium atom. So basically, electrons move between two levels in the cesium atom. When it's moving between these two levels, it does this number, and that is what is called, this is a transition between two levels. It does this number of periods, and that is what's considered to be, what is taken to be real time. Okay, fine. Are you following me? So it's really some phenomena that is more or less constant in physics, that is repeating, and you use it as a measure, a reference for real time. And this is, in this case, it is a transition between two hyperfine levels of ground state and a cesium and state. These are states of electrons that move between different levels. Okay, good. All right. So, but what is a clock then? That is time. So what is a clock? A clock is normally implemented by what we call an oscillator. Here is an oscillator. And a counter register. And these oscillators are normally quite precise. And it oscillates like a sine wave with a number of oscillations will reflect, like it's more or less can reflect real time in a sense. Okay. So what happens is that this counter register, it's incremented for each period of the oscillator. And as we said here, the oscillator frequency is not completely stable. It is very stable, but not completely stable. And it varies depending on environmental conditions. For example, the temperature, the age of the oscillator, and so on. So if you go and buy an oscillator for building your machine, then the manufacturer will tell you, okay, it will oscillate, for example, 1 million periods within a second, plus or minus 100 or 200 ticks, let us say. So the manufacturer specify what is called a nominal frequency and an error bound. an error bound. This is very important. Okay. So it will say in one second will be, for example, this is just an example. 1 second will be 1 million ticks plus or minus 100 ticks. Okay. All right. That is what. So the clock rate specifies how much a clock is incremented for each second of real time. That's good. So here is an example. The counter is incremented nominally by 1 million ticks per second. And that is what is used for measuring time. Okay. With an error bound by plus or minus 100 ticks per second. I think that that is fine. You following me? Good. So just a second here. Okay. So for our case, we will normalize the clock rate. Instead of talking about milliseconds, we'll say a clock rate is 1. And that is a nominal rate, okay? And the error is given by some parameter rho here. Okay, fine. For example, rho will be, in our example here that we showed before, rho will be 100 divided by 1 million, okay? Because we are normalizing everything to 1, okay? Oh, okay. So what does it say then? It says that with respect to time, so this is the rate of change of the clock by the rate of change of real time, will be between, just very easy, between 1 plus rho and approximately 1 minus rho, okay? You see this? So this is the rate of change. This is per second. So it means that a clock will drift. If it is faster in each second, it will be 1 second plus this 100 part per million, so a little bit. And if the clock is slow, it will say a second has passed, but it's 1 second less than this ratio. Okay, which is rho. Okay, so which would mean, what does it mean? If the clock is fast, we will get a time shorter than 1 second. If the clock is fast, if the clock is slow, it will say, when it says 1 second, it has really passed more than 1 real-time second. Understood? So you can go further. Okay. So now, what is the clock drift then? The clock drift is the accumulated effect of changes in the clock rate that differ from real time. So for example, if we have the x-axis is real time and in y-axis is the clock time, so if the clock say 1 second has passed when real time said the rate of change of the real time is also 1 second, then we have this equation basically saying that the rate of change of the clock divided by the rate of change of time is basically 1. Okay, and this is that line here. You can see it here, this line. If the rate of change is 1 plus rho, like here, the clock is fast. So, which would mean that when it says sometime here, it will say less, it will say, this is the time of the clock. It says now, for example, 2 seconds has passed when there is only maybe 1 second has passed here. I mean, if you have, I take the extreme. So in a sense, the accumulated clock rate has to be in this cone, if you can see it here, this cone. we don't know exactly what it is, right? So that is, so our clock will vary less or more time, but it is in this cone. And the more time has passed, the more the accumulated effect of the changes in the clock. That's why quite often you need to synchronize clocks in the computer. Okay, so that is fine. So let us see now, try to understand what is the effect of clock drift on the leader and in the follower, or on the proposer and the acceptor. This is two terminology. So we reason about what happens if the proposer, which is the leader, uses clock time instead of real time without compensation. So it means that his clock is going fast, okay, than real time, which would mean that the period he thinks he is a leader is shorter, which is okay. This cannot violate safety, as in this case, the proposer believes that his lease has expired sooner than it really did, okay? That is what this is saying. But the other alternative can violate safety here, which is the clock at the leader is slower than real time. So the proposer believes that it holds the lead even if the follower thinks that the lead has expired, you see. The follower might think that the lead has expired. And therefore, if he thinks he's a leader and his follower do not think he is a leader, then we will get to the situation that we had in that example. If he thinks he's a leader, there might be other leaders in the system, and therefore this read operation that we discussed when there was a partition could happen, okay? So in this case, the proposer may respond to a read, for example, as I said, and it might violate safety, okay? All right. So what this means? This means that the proposer or the leader, which is the proposer, must compensate by assuming that the clock is running slowly, as slow as possible. So he must think that the clock is going at a rate of 1 minus rho and compensate, okay? So this is, we can now see it, how this works. So what do we have here? If we just write it with a delta thing, so we have delta C divided by delta T should be equal 1 minus rho. Okay. And delta T should be less or equal 10 seconds, at most 10 seconds of real time. Then if you move the T to the other, if you move the T here, you get this equation, which say the delta C, the changes rate of the clock, should be delta T times 1 minus rho, which has to be less than this. So what this mean? It means that, in fact, the leader will keep the lease only for this period. The better the clock, the more it will approximate exactly 10 seconds, okay? But he's not sure, but because of his specification of the oscillator, so he should keep the lease for this period. So this is from the leader or the proposer point of view. So let us go back to the acceptor's point of view, which is the acceptors in the Paxos group. Okay. So what happens if the acceptor uses real-time clock? He uses clock time instead of real time, I mean, without compensation. So what happens here? That is actually, it will be the inverse. If the follower has a clock that runs faster than real time, So if a follower or an acceptor is the same thing, so that follower or acceptor will believe that the promise expired too soon. And therefore, he might be able to give a new lease to somebody else while the first leader is still there. And that will violate safety. But if the clock at the followers or the acceptors runs slower than real time, in this case, he will actually have it a little bit longer. He will stick with the current leader a little bit longer. So safety cannot be violated if the acceptor waits longer than necessary to give a new promise. So this is really how it is. And with the same reasoning, we will find that from the point of view of the acceptor or the follower, he should assume a clock that is running slower. So we should wait for a longer time. That should compensate for thinking that the clock is running fast. Sorry. So the acceptor must assume that the clock is running as fast as possible and should compensate, so he will stay longer. Okay. All right. So let's see what happens at the acceptor and at then the proposer. So the acceptor will actually, to implement just normal vanilla Paxos, will have another new state variable called tPromise. This is the clock time when he gave the last promise. Okay, this is the last time promise. And now, when the acceptors gets a prepare n message, n is a high number, okay, at time t. So t is our variable here. If n is higher than his current promise, and his clock at time t minus his promise is now past the period that he has promised before. So it's higher than 10 times 1 plus rho. Then he knows now he can give a promise to this new guy. Then he gave a promise to reject rounds lower than n and not to give any new promises until the next 10 seconds, okay? And he sets now tPromise, actually, tPromise to this current clock time at this time t that he got that. Otherwise, he will say, no, I'm still sticking with my old leader, so I will send you a negative acknowledgement. So we say, I'm not accepting that right now. Okay, so that is the behavior of the acceptor. The proposer, which is the leader, will also have a new state variable. I call it TL for T of the leader. So before he sends a prepare, and now the parameter is T, the time that he is doing these things, he will set this variable TL to the clock value at this time T before he sends the messages. And then he send the prepare. And if T gets promises from a majority, he knows that no other process can become a leader until 10 seconds after this time TL. So therefore, but what he is going to do, he is not sure about the accuracy of his clock. So he will say, as long as, so he will think that the period is not 10 seconds. He will make the period a little bit shorter. And as long as the current clock that I measure at any time t minus TL is less than this value, which is 10 times 1 minus rho, B can respond to reads from local state or any stateless operations, okay, in a sense. Okay, so this is the algorithm, and it can be shown here. You can see it appeared here. So P1 and P2, P3, we have a group of 3 processes. P1 sends a TL this time here. And that is what is his clock value at this time. He sent the prepared message. At time T1, P2 got the prepare. He sets his promise. He sets his promise to his clock at time T1. At T2, P1 now knows he is the leader. And at T3, which is, what is T3 minus TL? TL is this one. It is this period. That is what is T3. He will assume leadership during this period, as we said even in the discussion. Okay. So P1 knows he has a lease between T2 and T3 now. And I'm exaggerating everything. From the follower point of view, he's saying he's granting the lease until T4. And what is T? What is this period? What is this? It is the difference between his clock at this point minus the time he promised. So he is granting the clock for this period. So that is T. After that, P2 might grant a lease or leadership to other processes after T4. This doesn't. So if some other guy here wants to be a leader, even if he comes with a higher ballot number, he will get a negative acknowledgement. Okay. So
one question.
Yep.
So the raw value we had before, this is something we could see only externally, or is it also something the different processes could somehow know?
Can you say your question one more time?
The raw value.
The raw value.
Something which
the raw value is,
the
raw value is known in each processor, because in each machine, this raw value is actually given as a parameter to the. It is a parameter that the operating system knows. Okay. On each machine.
So is it?
You agree with me?
Like a value plus minus?
When you start this software on that machine, you will ask, you'll ask the operating system, give me row. You see. Do you see my point?
This row is a plus minus value? Because otherwise, I think,
yes.
Why does each process not just adjust this?
Why not? Because he doesn't know if it's a plus or minus. It's a plus or minus. Okay.
Okay, then it's clear.
You understand? Do you
okay, so
yeah.
Yeah.
I mean, he doesn't know. What is the manufacturer of the machine says our clock is inaccurate plus or minus 10 ticks, whatever, or something, or 100 ticks. You see, he has to take it into account. And it depends a lot if this is very negligible quantity or not. For example, in your systems, let me explain it in a different way. Assume that these machines are in a data center, okay? And in this data center, communication between different servers takes at least one millisecond, okay? If this row is so minor that it is some microseconds, maybe the algorithm will ignore it. It has to. It has to be in a context where it makes a difference. You see. Do you agree with me? I don't know who was talking, but can you? Maybe you can. So.
Okay. Yeah.
Yeah. All right. So you have to take into account this value in the algorithm. And you can get this value when you start your algorithm on that machine by asking the operating system about rho. And you cannot do anything because it is a period of uncertainty. It could be plus, it could be minus. That's why the leader assume the worst, or assume the leader assumes, like both as I discussed before, both the leader and the followers do the worst case of assumption here. You see, so that the leader will shorten his lease time a little bit, and follower will extend their lease time a little bit more. Otherwise, you have this problem of multiple leaders at the same real time. Okay, point. All right. So as long as the leader is somehow alive and well, he should remain a leader, right? So normally, not to lose the lease, so a process PI, that is the leader, who is currently the leader, before the period expires, he will ask for extension of the lease. Okay, so that is how. So in general, a few seconds before a lease expires, PI records the current clock time and asks for extension. And if the extension is granted by a majority, then what is going to happen is of replicas, then he will hold the lease another 10 seconds with the modification that we just mentioned. And the same thing happens with the acceptor. He will adjust the time for promise. All right. Okay, that's it actually for the time lease. So I guess the next lecture will talk about how to use clocks that are not precise. It will also talk about exact clocks which you cannot realize, but how going to use clocks that there is some guarantee interval about the deviation of the clock. The clock will not tell you exactly the time is t, but there is an upper and lower bound in this clock, how it can deviate, because there is some underlying algorithm in the whole system that tries to synchronize the clocks so that they cannot deviate, they cannot drift too much. And that will be using clocks in shared memory. And if you remember the algorithm for linearizability, then you will see that we can do a more efficient algorithm by the number of rounds it takes for both reads and writes, so that it will be just 2 message steps for one read and 2 message steps for one write when you use something called interval clocks. But let me show you something else I forgot to tell you. Yeah. Okay, so in Google data centers, they are using some form of Paxos consensus system. And in fact, they are using in that Paxos consensus a leader algorithm that uses time leases. So this is really are implemented in data centers. So this is just a side comment to what this lecture specifically. Okay, so we are going to end I will stop sharing.
I have a question.
Yes, and I will be here just for questions. Yeah, exactly.
Considering the latency of networks and the precision of the clocks or the hardware clocks,
yeah,
isn't the delay of the network greater than any drift will experience?
That is completely correct, at least in most networks, except if you are building an embedded system. You see.
Yes, but then right, because then it
yeah.
could be different.
Yeah, if you're building a system, say it will be on one board of multiple processors, and they want to do consensus between them. You see. Then the clock drift will be substantial, because the communication will be very, the latency will be very low between these processors. Okay.
Because I was thinking, even if you ping your own system, for example, you would still go through a lot of layers.
Yeah, that's what I said.
Introducing delays.
So I guess, this is a guess here, is that you don't, if the clocks are good enough, you don't normally take into account the clocks, because it might say instead of 10 seconds, it will be 10 seconds plus 1 microsecond or something, or 10 second, one microsecond less. And that will be negligible in a system where communication takes, say, 100 microseconds between machines. You see what I mean? Do you agree with me?
Yeah.
You see what I mean?
Yes.
So in this case, you wouldn't need to take into account the clock drift because it's negligible. Because anyway, communicating between two processors takes much longer time. You see?
Yes.
But if you build it in like an embedded system in a smaller set of machines, and maybe this is very tightly coupled. For example, currently now you will have chips where can have multiple processors, and you want to use these processors, and there is actually it is true. There are chips now who have thousands of processors, and each processor has their own memory. You see, and in this case, if there's a form of clock drift, you have to take care of that. You see.
So there are systems where the intercommunication between processors is so low, but the clock drift could be actually effectful between the communication.
Yes,
so
exactly.
It's important to know
for
about
this system, you have to take care of the clock drift. Otherwise, you shouldn't.
Okay, thanks.
So that is the answer. So, okay, guys, if you need anything else, you just tell me. Or now before I'm leaving, and it will be. I think the next lecture will be given by Paris, I guess, or Harald. I'm not sure. So we'll see. Okay, thank you for today. I will now stop the recording. Okay, bye.